and I'm in the center. And it's our great pleasure to have Professor Gaurav Sharma to come here to give our lecture about his recent work. He has already been here about 5 years ago, and I believe in these 5 years, there are quite a lot of new research has come out from his group. And a brief introduction about Professor Gaurav Sharma. He used to work in Xerox and for about 10 years, and up as a principal researcher and a group lead. And in 2003, and Professor Sharma joined the University of Rochester. And right now, he is a full professor there in the electronic and computer engineering. And he is the editor-in-chief in one of the most prestigious journal in computer vision and image processor area, which is actually transactions of image processing. That is a very high impact factor. And he is also a fellow of many different associations, such as IEEE fellow, and SPIE fellow, ISD fellow, and very famous guy in the entire computer vision area. And let's welcome Professor Sharma for his talk.
Thank you. So can folks in the back hear me clearly? Yes. So I speak loudly, but yeah, this room is also large, and I promise I don't bite, so by all means feel free to come ahead. Those of you who've had lunch with me know, and I can testify to the fact. So good afternoon, everyone. Thanks, Goyu, for the kind introduction. I'm going to be talking today of some of the recent work in my group. Last time I was here, I talked about the work more in the color imaging area, color and document imaging area. So this is going to be totally orthogonal to that. We're not going to overlap with that, except for some of the broader ideas and techniques. There may be some overlap with those. All right. So here's an outline. I'll begin with introduction, motivation, what I'm talking about, try and get everybody on the same page. Then talk about the work in different components. There are 3 main components. I'll not necessarily devote equal time to all the 3 components. That's just between the nature of progression of the work as well as the amount of time I've had to sort of integrate things into the slides. Okay. So I'll talk about the first component, which is real-time roadmap alignment to this wide area motion imagery. The second component, which is exploiting that for vehicle tracking. And the third part, which is trying to build in additional pieces of information by doing 3D reconstruction and georegistration at the same time. And finally, I'll end with some concluding remarks. Just to point out, the work has appeared in various publications that are listed over here. The tracking work is in fact something which was just accepted. And so this is the updated reference for this. I apologize, but I did not update the corresponding references in future slides. So there are subsequent slides where this reference will be out of date. So I'd also like to acknowledge this is largely the work of my PhD student, Ahmed El-Iti, who was with my group for a period of 3 years. And he worked largely on substantial parts of this work in terms of the vehicular the roadmap registration and the tracking. In the later parts of the work, Li Deng, who's a current PhD student in my group, has also participated. Okay. Highlights of other work may include samples from some other students. I'd like to try and begin with these acknowledgements. Usually I would put them at the end, but sometimes I would forget them, and that became sort of embarrassing for me later. All right. So, introduction, motivation. So we're talking about this particular type of imagery, which is referred to as wide area motion imagery. So this is actually something which harks back to a talk here given by Bernie Brower at the Center of Imaging Science several years back. When he was presenting is the time when Ahmed was looking for problems to work on, and I gave him the suggestion that this may be a great area to work on. So this is a system which is this wide area motion imagery sensing system. They will usually have an array of cameras mounted on a plane, which will fly and capture a series of images which capture fairly substantial areas. So this is, they call it city scale, several square miles is what each frame will be captured in. And the frame rate, however, is fairly low. It's about 1 to 2 frames per second. So here's an example. This example is a sample of pixels, and this is from the Rochester region, captured actually with the system from Corvus I. This is now part of Harris. This is what originated with Kodak, then went on to XLS, and is now part of Harris Corporation. So to give you a sense of scale, this is the distance of about a mile across over here. And to give you a sense of the resolution that this data has, this is that frame that you saw in the previous slide. And this is a blow up of a small region of that frame, showing you the level of spatial detail that we have. So what we've got is high spatial resolution. The spatial resolution allows you to resolve things like building features, what these buildings are, individual vehicles, roads, trees, and a variety of other things. Our particular focus in this will be the vehicles, and we'll be looking at both using these vehicles for aligning the roadmap precisely with this imagery, as well as for tracking the vehicles. So this is a new type of imagery, relatively new in terms of the existence of other types of images, and this is enabling a whole set of new applications. The key aspect here is this is a large scale. You're capturing substantial geographical areas at one point in time, rather than having small images or small regions. It can be near real time and potentially interactive. So if you could have a downlink, the downlink would typically be limited in bandwidth, so you could not possibly convey the entire information. But if there's a region of interest, you can arrange that that region of interest is being communicated real time to you as you're following this. Okay. So as with most things, new systems also enable new applications. Clearly there's interest in this for security and surveillance. This is where there is the application to vehicle detection and tracking. If you have a real-time event going on somewhere, you would like to track the vehicles and figure out whether there's any unusual activity or any unusual pattern of detection. So this is something of interest in security and surveillance. However, that's not the only realm of application that you can imagine for this type of technology. If you're trying to do resource planning for a city, and you're interested in finding out which are the major bottlenecks, what are the sources of bottlenecks, then this is something which can be used, the same imagery can be used for that purpose in terms of analyzing the traffic patterns, as well as because these imagery is captured from an oblique viewpoint, you can also construct some 3D information about the 3D structure from this. And this is just sort of one chosen set of applications which I'm going to draw from, but the applications for this data sets are actually quite numerous, much more larger than what I'll be talking about in this presentation. So what are some of the challenges associated with this type of analysis? So what I'm showing you over here is two subsequent frames from this WAMI sequence, where we have compensated for the global camera motion between the two frames. That's fairly well-known technology in computer vision today. You can find corresponding features in the frames and align those, and then compensate for the global change between those two frames. So what you can see is that the moving objects are largely the vehicles. The vehicles pop up as the moving objects over there. However, what you can also appreciate is that you're dealing with a large number of vehicles. So the scope of the WAMI frame that you're looking at, you have hundreds of vehicles. So this is very different from the typical target tracking problems you would think about in terms of human tracking, where the number of targets is extremely small, typically. You're not talking about more than maybe 15 to 20 targets at most. In our case, we're talking about of the order of hundreds of targets. Okay. The data rates are extremely high. So if you look at the WAMI data stream, you're dealing with about 1.25 gigabits per second in the compressed format. In this case. The temporal frame rate is fairly low. So typical motion video that you look at, which you capture with your camcorder, would be about 30 frames per second. Okay. This is about 1 to 2 frames per second. So compared to full motion video, this is a fairly low frame rate. What are the implications of that? If you're taking full motion video, normally the object will overlap in subsequent frames. So if you're looking at an object over here, in the subsequent frames, it will largely be in the same position. There'll be some strong overlap between that. However, in this situation, because the frame rates are relatively low, these objects between subsequent frames are non-overlapping, and also the association between which one associates with the vehicle in the previous frame is not necessarily immediately apparent. Okay. The vehicular spatial detail is limited, except for these highway trucks that you see, except for the large trucks that you see. Most of the other vehicles appear as little specks, and you really can't distinguish them by their appearance. So you can't say this is this particular make or color of vehicle, and therefore associate them by that way. Okay. So you have to think about techniques, if you're going to process the vehicles, techniques which are not particularly relying on distinctive characteristics in the appearance of the vehicles. And this will be key to what we talk about. Finally, also importantly, is that the imagery can be captured with multiple modalities, including nighttime IR. So the advantage of these platforms is that you can capture imagery not only in the daytime, this is RGB imagery captured in daytime, but also in nighttime you can capture IR imagery. And ideally, if you're developing a technique, you'd like the technique to work even in that imagery. Okay. So that will touch on each of those. So our approach in tackling this problem is one which is driven by more of the availability of large amounts of data. In particular, if you're tracking this problem, if you're addressing the problem of vehicular tracking, then one resource that's available to you is roadmap information. So these are becoming increasingly common and increasingly available as open resources. One of the common sources of maps is this georeferenced road maps known as OpenStreetMaps. So this is an open revolution in terms of trying to map the roads openly. And in a lot of areas, these are actually ones which are updated and used more frequently than the closed resources that companies have. So for instance, there was an earthquake in Nepal a few years back. The volunteers that were participating in the mapping experiment could quickly update the OpenStreetMaps to see which paths were still viable and come up with routes for routing, whereas the commercial companies were not able to react as quickly. Okay. They have mapping workshops all over in different parts of the world, and the resource is only building up to gain strength over time. Okay. So our approach is one which is motivated by trying to align this roadmap with the captured imagery in order to use this more effectively. What can you hope to do by that? So if you look at the typical highway separated by a median over here, as you see, then in this situation, you know the direction of travel. That simplifies your problem of tracking. Vehicles on one side will be traveling in this direction, vehicles on the other side will be traveling in this direction. So in order to do that, however, the key requirement is that our registration needs to be what we call pixel accurate. If you're just relying on what you've got with the GPS and INS, that gets you in the right ballpark, but is not necessarily of the same level of accuracy that you would need over here. And I'll show that as a result in the subsequent slide. So our goal in this work is to bring in auxiliary sources of information to simplify the scale of the problem and to make it more tractable. In particular, we'll be looking at using georeferenced road maps as a source of auxiliary information. And I already touched upon this. By knowing the direction of travel, you can simplify the tracking problem, which is what we'll be doing subsequently. So the first part, I'll talk about accurate real-time roadmap alignment between a roadmap and the captured imagery. So this is the framing of the problem. Typically, the roadmap is represented in some vector format. That's what is commonly used for OpenStreetMaps. This is showing you this. These are normally represented as segments of lines between certain control points and indicating additional metadata information for those segments, such as direction of travel, whether they're one-way, two-way, and so on. Okay. And what you have over here is a captured WAMI frame. This is now an oblique viewpoint, not quite the same orthographic representation that is commonly used for these representations over here. So you've got fundamental mismatch between the type of representation you're using over here, which is a vector representation, and a raster representation of the image that you have over here. So you can't easily think about matching features in these components. You'd have to have some sort of high-level semantic understanding to see what are intersections and then try and match to that, and that's a challenging task still in image understanding. So this is the framing of the problem for the registration. We've got the captured WAMI image, which is a raster image, some Cartesian coordinates. There are a different set of Cartesian map coordinates, typically azimuthal orthographic map projection, which is also referred to as a affine camera in this space. And our goal is to find out a transformation which will take us from this coordinate system to this coordinate system, aligning the road network in the captured imagery with what you have over here. So our goal is to estimate this transformation. In particular, the type of transformation we'll estimate is what is referred to in computer vision as a homography. This is what applies when you're imaging a planar region with two different cameras. You can show that when you're imaging a planar region with two different cameras, a homography can allow you to transform between one view and the other view in terms of the geometry. So how do we do that? We actually exploit the vehicle motion to our benefit in doing this. So this is showing you the sort of overall structure of what we're doing. We have successive frames. We can align these two frames that I told you already is fairly well-known technology in computer vision today. You'll be looking for corresponding features between these two frames. I say that problem is easier compared to the problem of finding corresponding features between the vector road map and the raster image. Why? These are both taken at the same time, The viewpoints only change slightly to the extent that the camera has moved. So this problem is fairly easy and robustly tackled with current computer vision techniques. Once I've estimated the global change in viewpoint between these two, I can compensate and remap the data from one frame to the other frame. So this would, what that would represent in words would be the image that would be captured from the same viewpoint at the point of time that the second image was captured. So what you're doing is keeping the time coordinates the same, keeping the spatial coordinates the same by compensating for the spatial displacement, and the temporal coordinate change is something which is obviously not something you are compensating for. This is what you call the compensated frame difference. When I've compensated for the global motion, computed the difference, the things that will stick out, is there some way to turn the lights off here? Is this the lights?
To your left.
To my
Just
left?
hit the bottom button on.
This one?
No, down lower, the green button.
Oh, this one over here? Oh, it's the other way. Turning the lights on and off.
If you hit the bottom button on the one on the top, it will turn them all off.
We'll turn the other ones off, but maybe one about this. Yeah.
The one you started to hit, the switch up top.
Oh, this one?
Yeah, hit the bottom button on that. That should shut them all off.
Oh, yeah. Oh, so this is what I wanted you to see. So I apologize, the contrast here does not seem to be the same as on my display over here. So people can make out?
Yeah, we can see it.
You can see it?
Yep.
So what those are the locations where, after I do the global motion compensation, this is where things have changed. So by and large, what pop out over here are the moving vehicles. This is where things have moved. So the vehicles pop out as the changes, because if I was to taking the same, from the same viewpoint as we're taking two images at 2 points in time, the vehicles which have moved will be causing changes in the image, and that's what is visible over here. This is what we will take as the vehicle detections. We will align this with the roadmap and come up with this transformation to align. Once we have this alignment, we can now remap the image according to the coordinates transformation that I need to do and get an alignment of the road network with the image that we have. So the motion of the vehicles is something we are advantageously using over here as a way to detect features and align them. By doing this approach, we don't have to try and compute features which are invariant across the different representations. The vector representation of the roadmap here and the raster representation of the images over here. So this is showing you the same thing. What is the compensated frame difference? This is the reference frame. This is the second frame registered to this. If I toggle between these back and forth, I don't know if people can see in the back, the vehicles are what are moving, because the global motion of the camera I have compensated for, and what is then remaining is the local motion of the vehicles, and also some other motions which you will not be seeing in this, but I will talk about later. By the way, I should have said this at the beginning. If you have any questions, please feel free to jump in. I'd rather keep this interactive rather than. So this is what you get with the compensated frame difference, and I highlighted this already, that the vehicles pop out as the moving objects. So these are giving you a guide for what you want to align. Now our problem is one of aligning these vehicle locations. So the good part is the vehicles normally go on the roads. So if you align the vehicle locations with the road network, at least in the United States, maybe if you're traveling in India, things may be slightly different, but you want to align this vehicle locations with the roadmap. So now at least our problem is simpler. We've got a binary image here and a binary representation here, and we would like to align this with this and find out the transformation. To help us, we can also use the initial alignment, which is already available with the metadata for the wide area motion imagery. So the wide area motion imagery typically includes GPS and INS information, which gives you gets you in the right ballpark over here. So our goal is to try and estimate a homography to go from here to here. So what we use for this is something known as chamfer alignment. This is a fairly well-known tool in computer vision, maybe not as commonly used for alignment type of problems. More commonly what people tend to use is feature matching, but chamfer alignment is actually also a fairly powerful tool, and for this case it's actually well suited So to formulate this, I'll describe what we formulate as a chamfer distance. Okay. So these are the locations of the vehicles. So this is the V stands for vehicle. This is the jth location of the jth vehicle. And for each vehicle, I would like to see that its positions after I do the transformation should be close to the road network. Okay. So for each vehicle, I will formulate the distance that I get. This is the transform location of the vehicle under the parametric transform. This parametric transform will be my homography. So I'm transforming this under an assumed transformation between the coordinates of the two images. This is my transform location. For each one, I would like to find out what is the closest point of the road. So the notion is that the vehicles normally go on the roads, but wherever you have a road, you do not necessarily have a vehicle. It's one directional, so you have asymmetry in the matching. So formulation of this is, I have a distance between the transform location of the vehicle and the closest point on the road network. So R is for the road network. I will have variety of roads, also different segments in the road. I'm looking at the minimum across all of those segments and the different roads of what is the closest point to my transform location for this. And I'll take the sum of the distances over all the vehicular detections that I have in this case. So these are all my vehicle detections. For each vehicle detection, I'll take the perpendicular distance to the closest point on the road network and sum the squares of those perpendicular distances. So this sounds reasonable as a way to align. However, as a computational technique, this sounds quite nightmarish. Okay. And what simplifies this is something known as the distance transform, which once you know the idea is actually quite simple. Okay. So what is the distance transform? I can pre-compute distances from the road network to every pixel as an image. So that's what I'm showing you as this background grayscale image. The distances of 0 are encoded as black. The maximum distances are encoded as white. So when you're on the road network exactly, this distance will be 0. So for every pixel over here, I have pre-computed a lookup table which says what is the closest point in the road network. And there are efficient ways to also compute this distance transform. Okay. Now the problem of computing a metric becomes really simple. I simply have to look up at all the yellow points, what is my value, and sum those up. So the distance transform really simplifies this process of estimating what is this metric. Now, in order to do this, we would like to actually find what is the best parametric transform, or equivalently, what are the best parameters of the homography that we would like to have for aligning that. And for that, we use a numerical optimization technique. This is simple least squares, nonlinear least squares, 11-Marquardt optimization. And I did not highlight this, but to enable this, we can actually not only do what I showed you with the metric, but I can also do with its derivatives with respect to the parametric transforms. So the derivatives also for the parameters of the transform can be obtained by the same lookup table technique that I highlighted over here, allowing you to do this fairly efficiently. So this is our formulation now. We've got the road network, we've got the vehicle detections. We go successful iterations. This is the first iteration, starting from the initial point. So my encoding here is the green points are the initial vehicle locations. These are the aligned vehicle detection locations for the current estimate. This is the road network. So I'm at the first iteration, second iteration, so on. And you see as I proceed through the iterations, my vehicle detections nicely align with the road network, giving me a good alignment with this. So this is my optimal estimate alignment. This is showing you what the alignment looks like when I superimpose the road network with the imagery, and you can see that we've got a fairly good alignment between the road network and the imagery. Now, one thing I did not mention over here is this depends on how well you detected the vehicles originally. So if you look at the compensated frame difference, this is what I talked about earlier, this is how you are detecting the vehicles. Depending on what you choose as your threshold for detecting something, you will either detect this number of targets, or if you choose a lower threshold, you'll detect a larger number of points. So if the quality of your detected vehicles is poor, if you have too many spurious detections, then your alignment suffers. So how can you address that? So that's the second component of the work. So to motivate this, think about it. If you knew which one were the spurious detections, you could easily exclude them in the alignment with the road network. If you had the alignment with the road network, correspondingly, you could figure out which one this is the spurious detections. Okay. So this is the classic chicken and egg problem. If I knew the registration, I could figure out which points to exclude. If I knew which points to exclude, I could figure out the registration. So to address both of these simultaneously, we use an iterative probabilistic technique. This is a technique in machine learning known as expectation maximization. This is a common algorithm which several of you may have encountered in your research. It's very broadly used in a wide variety of applications and has been discovered in multiple contexts separately. So the EM formulation will model a probabilistic framework and use ML maximum likelihood estimation. So we expect the on-road vehicles to be close to the road. So we can model this via an appropriate distribution. The distribution we use is an exponential fall off with distance from the road. The challenge is that a detection may correspond to an on-road vehicle or may be spurious. So we cannot directly model the distribution of all vehicles as concentrated on roads. So to address this challenge, we introduce a set of latent random variables. The latent random variable is for each vehicular detection, indicating whether we think this is on the road or it's spurious. So for on-road vehicle detections, the latent variable will take a value of 1, and it will take a value of 0 if it's spurious. And we assume that this distribution is IID across the vehicle detections with unknown parameters. The parameters are something which we inherently estimate from the process. So this modifies our formulation to address this. The modification that we have compared to what I've motivated earlier is just a weighting factor. Instead of formulating the metric as the sum of these minimum distances from the transformed locations of the vehicles to the closest points on the road network, instead of that sum, you have a weighted sum. The weighted sum is the weight is just the posterior probability. Pj is the posterior probability that the jth detection corresponds to an on-road vehicle. So the intuition behind this is, if this is an on-road vehicle, you would like to have to count towards the metric. If it's not an on-road vehicle, you would like it to not count. For an on-road vehicle, we would like this to go towards 1. For an off-road vehicle, we would like this to, or for anything else, we would like this to go to 0, discounting the part. So here is showing you different cases of things which are on-road and things are off. So you can do this by weighted chamfer minimization. The rest of the framework carries over for the weighted chamfer minimization. In addition, we have the EM iteration embedded in this process. So the way the EM iteration works is that we alternate between estimating the posterior probabilities of each of the detections being on-road vehicles with an appropriate probabilistic model, and re-estimating the alignment by minimizing the weighted distance. So you have these two inputs, the set of detections that you have and the vehicular network. We will estimate the alignment. We will alternate between updating the posterior probabilities and also the distribution parameters and estimating the alignment. And then we will get something which is closely matched with the road network. So we iterate between these two. I will highlight updating of the posterior probabilities. This is showing you how the posterior probabilities get updated as you proceed through this steps. And I'll highlight a particular region over here. You have over here. So this is maybe early in the process that you have. So you will have high posterior probabilities for everything. At this point in time, you do not really know what is on the road and what is off the road. As you proceed with iterations, this is the final posterior probabilities. So you see the final posterior probabilities are pretty high for the vehicles on the road, but the ones which were other things, not quite on-road vehicles, the posterior probabilities are low. So by formulating this framework, we are able to overcome the challenge of spurious detections. This is what the final line result looks like, and the method is fairly robust against your threshold that you choose for what you declare as a vehicle, for the reasons I outlined earlier. The more details, additional details, I'll refer to you for the published paper on this, in terms of how we formulate these as appropriate probability distributions in this case. So how does this compare? So to highlight this, I will compare this 3 alternative techniques. MBA is what we call as the metadata-based alignment. This is simply using the metadata that you have from the WAMI imagery from the GPS and INS to align the road network with the imagery. SPA is what you would traditionally think of SIFT-based alignment. So SIFT is a common feature. Several of you may have seen SIFT. It's very extensively utilized in computer vision. It's called the scale invariant feature transform. That's a technique for trying to match features. I've already told you that it was not possible to match features between the very different representations. So in order to do the SIFT-based alignment, we actually rely on Google Maps as an intermediary. Since the Google map is at least raster imagery, we have a way of trying to find corresponding features between the Google Maps image and a captured imagery over here. The last one is our proposed, and you can see that the metadata-based alignment, even though that gets you in the right neighborhood, is not quite accurate enough for you to be able to use it in tracking. This is not quite aligned with the road network, particularly if you're looking for direction of travel. You will often be looking at the wrong side of the highway being aligned with the imagery in this case. To compute this, so visually you can see that the proposed technique does much better than either the SIFT-based alignment or the metadata-based alignment. To compare it numerically, we also computed the chamfer distance in pixels for each of the technique. So this is what I motivated earlier. This is the sum of squared. So this is actually not sum of square distances, but sum of absolute distances between the points and the closest point on the road network. So our proposed technique is about 2.07 pixels. SIFT-based alignment is about 83 pixels. Metadata-based alignment is about 122. So it's not substantially, the SIFT-based alignment does not substantially improve upon what you've got metadata-based alignment. Here, other sample alignment, same story here. In this case, the proposed technique does quite well and aligns this fairly accurately with the road network, allowing you to then subsequently use it. And since our technique is relying only on movement of the vehicles, it's agnostic to the type of modality you're using for the imagery. So this is showing you the same thing for infrared imagery, but the moving vehicles also appear as moving specks in infrared imagery. Since your technique is only relying on the vehicular motion, it works equally well for infrared imagery. The SIFT-based alignment there particularly fails because the modality of the images is completely different. So for you to match those is extremely challenging. That's still one of the big open problems in computer vision, is cross-modality matching of features. Any questions on this part? Sure. Jeff.
How does this compare to doing something like ransack to exclude the spurious matches?
So we already did ransack. When you talk about SIFT-based alignment, that actually includes ransack in the formulation.
Okay.
So instead of formulating, there are two alternative approaches to alignment. One is using sort of a global metric. That's what we're using. We're asking for globally, what is the cost of aligning all these detections with the road network? The other alternative is to use features and to have corresponding matchings. So the challenge with, I'll highlight that further also in the presentation. I think I have slides on that, highlighting some of the reasons for that. Might be not coming up right away. Maybe you don't have that in this presentation, I apologize. But I'll be glad to speak with you offline.
Okay.
The challenge is that lots of things change. You're looking at these from oblique viewpoint, different times of the day. So trying to match features with SIFT just does not work, even if you're trying to do this in imagery to imagery. So, all right. So this is showing you the final posterior properties, as you see, on a scale from 1 to 0. What you will see is that the final posterior properties for all the detections which line up with the vehicular network, with the road network, are quite high, whereas for points which are further away from the road network, all of these go to a small value. So this highlights the advantage of using the EM framework. And this is happening automatically. This is not something we are manually classifying vehicles. This is happening automatically through the process of using the expectation maximization iterations to estimate this. Maybe in the interest of time, I will try and skip the animation. I had an animation I could show on this. Should I try for that? So this is showing the same thing as an animation. Reload the image. The reload option. Do not typically use. Okay, it is. See the animation how it's proceeding over here. Oh, proceeds, yes, it's slowly. You see that how it's proceeding? As the animation, as this is proceeding through the steps, what you will see is that the probabilities for points which are further away from the road network will be going down. So these points which are further away from anything on the road network, they will be decreasing in intensity, whereas the ones which are close to the road network will increase in intensity. So you're waiting essentially to exclude the points which are not on the road network, include only the ones on the road network. So in the next stage, what we worked on this was also to see if we could do this in real time, because you're trying to use this for tracking. The interest in trying to see whether you can do this in real time. So I will just summarize this by saying that we can obtain a significant speed up of this parametric chamfer alignment by parallelization, because you have independent and similar calculations for each vehicle. So this is nicely parallelizable on a GPU. Additionally, we also introduced an idea of pipelining, which exploits the low arithmetic latency for GPUs compared with the memory latency. So the high memory access latency means that if there's something, a computation that you may possibly require, but you're not sure if you require, it's better to do the computation when you have the data in memory, and if you do not require the result, discard the result, rather than try and fetch the data again later. Okay. So there are the two components that contribute to this part of the work, but yeah, this allows us to do real-time performance for alignment roadmaps. This is also applicable to other multi-dimensional data sets, in particular for 3D data and point clouds from buildings. So this is showing you this performance for the alignment of the wide area motion imagery to the road network alignment. This is performance for an unoptimized CPU implementation. This is the performance for an optimized CPU implementation. This is what corresponds to real time, 500 millisecond, which is the interframe duration. And this is what is our optimized CPU implementation. So we can allow this to accomplish this in real time using the GPU implementation. I highlighted this. We can also do this for 3D models. We had an interesting project on architectural biometrics, which I will not have time to, but the same kind of technique also applies in that setting. Questions on this part? Sure.
Have you ever tried using ICP for the alignment?
Yeah, so the ICP corresponds to more of a harder classification between alternating between whether it's on the road or off the road, whereas this corresponds to more of a probabilistic. So yeah, so as compared to the ICP, I think we do better by using this framework.
Okay.
In addition for the ICP also, you would have to have some way for formulating. So I did not highlight this aspect. So in the starting point, when you start by looking at this, your confidence in terms of what is near the roads and what is away from the roads is low. So when we model it as a probabilistic distribution, we model as an exponential falling off on either side of the road. That exponential is modeled as fairly shallow in the starting point, and the parameter of fall off is something we learn as we proceed. So as we iterate, our fall off becomes more pronounced but as things align well. So that has the advantage that I highlighted earlier, that your weights are really concentrating on the points that you want to use.
Sure.
Okay. So at the final stage, you could do ICP, but at that point, you already have the answer.
Yeah.
For those of you who might not know ICP, ICP stands for iterative conditional point, which alternates between classifying the points as zeros and ones, and then the registration process. So the next stage, I'll talk about vehicular tracking using the road network in this setting. So I already highlighted some of the challenges for tracking in this setting. You really do not have much appearance information. You cannot say this vehicle is the same one from one frame to the next. So this is what you refer to as tracking by detection. You're given a set of detections identified by their locations in the series of co-registered frames. And your job is to try and associate what are the hypothesis tracks that you have by associating these detections across the set of frames. So the contribution of our work in this area is an iterative stochastic progressive approach for estimating tracks, where these iterations grow the temporal context, which is the number of frames, for improved accuracy, and then manage the computation by limiting the number of association hypotheses by exploiting both the aligned road network and also stochastically retaining some part of the associations already found. This allows us to get significant performance improvements over the state-of-the-art methods. So, When did we start? How much time do I have?
Like 15 minutes.
I have 15 minutes? Okay, so then I'll try and go faster. Maybe give you a high level view of this. Is this okay? So tracking is a very old problem. People have been tackling it for many, many years, many decades. And so it's sort of, the question is, what new can you do in this context? So our particular realization is, in our situation, what we're doing is, we do not have much information about the vehicles. All we know is what are the locations. So if you're going to track things based on locations, your only bet is you want to use some model for vehicular motion. You expect vehicular motion to be smooth, and you'd like to estimate what are the smoother tracks. Okay. Now in order to estimate smoothness, if I have 2 points, I can always fit a line between any 2 points. So to estimate smoothness, I need things more than 2 points. Okay. So if you use more than 2 points, the issue becomes that if you want to estimate, formulate metrics for cost of a track based on more than 2 points, the cost does not dissociate into adjacent frame costs. And that makes the problem intractable. From a graph theoretic perspective, this problem is known to be NP-complete. For those of you who were at lunch, I was pointing out to you that when I was in graduate school, if somebody said a problem was NP-complete, you worked on something else. The world has changed since then. Now you have algorithms which work on NP-complete problems and give fairly good results. So this is an example of that. Okay. So I will probably, in the interest of time, try and not talk about details of this. Essentially what we're doing is looking at all possible hypothesis tracks and looking at associations that we are forming, starting with an initial point, and then revisiting the associations which we have low confidence in. So maybe the next slide will be the one which will be useful for highlighting this idea, instead of talking about the details. Okay. Yeah, there is prior work on this. The prior work addresses the situation where the costs are decomposable into a cost per stage. When the costs are decomposable into a cost per stage, you can find efficient algorithms which allow you to compute these optimal tracks under this setting. And there are also other techniques which try and do this with probabilistic graph matching. So the local context of an object should be the same as the local context in the matched region. However, these techniques do not scale to the size that we're talking about in this case, the larger number of vehicles. So maybe I will highlight this by means of a okay. This may be the slide which I want to speak to. Okay. So how do we formulate the problem? Okay. So this is where this problem has been previously addressed. What they will do is they will keep all the associations fixed and reroute the associations between two adjacent stages, keeping the other ones fixed. This is a class of prior algorithms that have been used. Okay. The challenge with this is once you get caught in a local minima, you do not manage to get out of it. What our approach is doing is that we will use this. Okay, this is the highlighting our approach. Okay. We will begin with a set of associations. So the associations here are associating what forms a track. So 1, 3, 3, 1. So what I'm labeling over here are the detections in a frame. So over here are my frames. This is showing you a sequence of 12 frames over here. Over here, my vehicular detections in these frames. And the associations, which are the red arrows between the detections, are what you're formulating as hypothesis tracks. So I'm assuming this is a single vehicle, which in frame 1 was detection 1, and frame 2 was detection 3. Frame 3 continued as detection 3, came back to detection 1 in frame 4, and so on, forming a complete track. Obviously, there are constraints between these. The same detection cannot be allocated to 2 tracks, for example. So there are constraints that you need to take care of, which is what makes this problem challenging. Okay. So we assume that we start with an initial set of estimate of tracks, this type, and then we iterate. How do we iterate? We estimate a confidence for each possible association. So for each association we have, we estimate a confidence in terms of what is the confidence that you have that this is really correct, or you do not, what is the level of confidence that you have that this is correct. Okay. Now we dissociate according to the level of confidence. So the association over here is retained with the 1 minus the probability of confidence that you have in that association. So if you're completely confident in an association, you retain it completely. If you're completely sure it's bogus, then you will dissociate it completely. And things in between will be accordingly scaled. Okay. So this leaves you with some existing associations and a set of free detections which you now need to associate somehow. So to estimate these, we will now compute all the possible road network hypotheses, hierarchically dissociate this. Doing this over the full set is quite challenging. We will do this over a hierarchical set, meaning that I'll partition the problem into smaller sets and evaluate all the possible tracks which are valid, feasible tracks for each of these sets, and then choose the best option among these. Once I have that, I can do this hierarchically across not only individual subsets over here, but across the subsets over here to link and obtain my next iteration. And I can repeat the process. Okay. When I repeat the process, I will grow the context. So I'll do exactly what I talked about, estimate confidence, dissociate based on confidence, estimate hypotheses, but now I will be using a hierarchy with an enlarged context. So I'm using larger context. What's the intuition over here? Since the only information that we have is motion smoothness, by incorporating a larger geographical context gives you better information, using more of the information. This process. All right. And once this is done, you can proceed the same way, increasing the context. So this is what we call stochastic progressive association across multiple frames. The stochastic part is our estimation of confidences and deciding what dissociates. The progressive part is that as we go from one iteration to the next, we are enlarging the spatial context that we're using. And the rest is really the problem statement, association across multiple frames. Okay. So how did this perform? I already gave you this idea of the algorithm. Okay. All right. In doing this, we're actually using the aligned road network, and that actually provides crucial pieces of information. This is showing you just this by means of an example over here. So what we're using in our association of motion smoothness is road travel distance, is one of the components. So for instance, if you did not have an aligned road network, the distance between this vehicle over here and this vehicle in subsequent frames, this might be preceding frames, I forget whether this is preceding frames or subsequent frames, I think these are subsequent frames. So if you're looking at this vehicle in a frame I2, and in the next frame I3, you're looking at these possible associations. In the absence of a road network, you don't have any way of distinguishing which one is more likely or less likely. However, in the presence of the road network, you know that the road travel distance from here to here is too large to be traveled in this time frame unless the driver decides to drive over the side of the ramp. Okay, so excluding those wild cases, you can form the association. You can associate a pretty low probability with this association and formulate the prune the road hypothesis that we formulate. So to do results on this, there's a variety of data sets. We use the data set, which is the Coverside data set from Rochester, New York, to Wright-Patterson Air Force databases. These are put out by the Wright-Patterson Air Force Base in Ohio. And this is showing you sample images. I'll call these sequence 1, sequence 2, sequence 3. They will both have their different characteristics. This ground truth data that the Air Force provides for the data set. For our own data set, we actually annotated ground truth. And for this, Ahmed did quite a bit of work developing an API which allows him to annotate this by building it upon top of what is referred to as label meaning for labeling these. We compared several techniques. The proposed technique, which we call the stochastic progressive approach. Proposed technique where it's non-iterative, using a single iteration of the proposed without the stochastic dissociation. Iterative global tracking, which is using the same cost function. So what you're optimizing is the same metric, but the algorithm is different. It's revisiting the associations at one stage from one frame to the next while keeping the other ones fixed in this case. And we also consider two online methods that use the pre-aligned road network. Now in tracking, there's a wide variety of metrics that have been used. So I'll sort of illustrate these metrics by highlighting them in this slide over here. So this is mostly tracked. Mostly tracked vehicles are the vehicles for which more than 80% of the frames will have detection associated with the track. Mostly lost are the converse, which have less than 20% of the frames have an associated vehicle with the track. Partly tracked is everything in between, these two. ID switches are switches where, so this is illustrating something which is mostly tracked over here. So this is showing you the estimate track, ground truth in blue. So this is the ground truth, this is an estimated track. So this is something which you would consider mostly tracked. This is something which you would consider mostly lost. So your estimated track is a very small component of the overall track. ID switches are situations where the ground truth tracks are like this. What you estimate is like this. This is a common thing when vehicles go through intersections. You swap the associations between one and the other. So the arrows here are indicating whether you like this to be high or low. So you would like mostly tracked to be higher, mostly lost to be lower, ID switches to be low. Fragmentation is where a trajectory gets broken up into two fragments over here. You would like those to also be low. So this is showing you the quantitative results for different techniques. This is on the different sequences. This is the number of ground truth tracks. This is the number that correspond to our different categories: mostly tracked, mostly lost, partially tracked, ID switches, fragmentation. In the interest of time, maybe it's just worth focusing on the ID switches. If you look at the ID switches for the other two techniques, they're fairly large. The proposed technique, they're fairly small. So compared to the initialization techniques, we've done a significant improvement. Same thing in sequence 2 and sequence 3. The online methods perform worse on sequence 2, and the reason for that is because it has several two-way roads. It has several two-way roads. They're not able to distinguish between the association between the vehicles traveling in one direction and those traveling in the other direction. They're in close proximity to each other. Sequence 3 is easy. All the methods perform well on sequence 3. Sequence, yeah. Comparing the proposed method against another technique which is using the same metric and a different technique. This is iterative global tracking, is what we call that. This is showing you the comparison over here. This is the initialization technique that's used for both techniques. This is the technique IGT, initialized with an online technique, the proposed technique initialized with this. And again, focusing just on the ID switches, you will see that the ID switches that we get with the proposed technique is significantly lower than what you get with both the initialization as well as the iterative global tracking. In particular, the iterative global tracking does not really improve substantially upon the initialization. There is a small improvement, not really substantive, and that's because of the problem of local minima that I highlighted earlier. You're revisiting only the one association while keeping others fixed. This is highlighting the same thing. This is showing you the cost function for iterative global tracking versus the proposed technique as a function of iteration count over here. You can see the proposed technique, by using the enlarged spatial context, rapidly improves the quality of tracking, and the metric goes down, whereas the iterative global tracking gets stuck in a local minimum over here because it's only revisiting the same decisions. This is runtime. In the interest of time, I will skip that. So to summarize, I talked about the tracking problem by the emission machine imagery. The two components that we brought to bear to make this computationally feasible was this idea of using the road network aligned with this to prune what set of hypotheses you need to visit, and also to utilize this idea of an enlarging context and stochastically retaining a subset of the associations and revisiting only the low confidence ones. Okay. So the idea is the enlarged context provides you better information for revisiting these associations which you did not have confidence in. And these results show significant improvement over the prior state-of-the-art algorithms. Finally, I just mentioned briefly, we have done further work since then, which is looking at 3D georegistration. The technique I talked about for registration was fairly good for the road map, and that's because the roads are normally close to a planar surface. They're not completely planar, but there are no roads going on the sides of buildings, at least not yet. Okay. So, whereas you do have sides of buildings. So when you're trying to register things which have these vertical rises from this oblique view imagery, that becomes fairly challenging. We have a framework which tries to leverage what we already have in the registration and use techniques in computer vision, in particular geometry-based vision, to try and register these in a 3D coordinate rather than 2D. So this is showing you what you had based on metadata. This is what you would get using just the two-dimensional technique using the road network. And this is what is including the 3D information from the point cloud reconstructed from the same data. This part, I apologize, in the interest of time. I have really cut this part out, but yeah, I'd be glad to speak with you for details of this. To summarize, I talked about problems in wide area motion imagery. This is a rich source of large-scale visual data and also enables new geospatial analysis. So I think the power of this analysis is actually further magnified by the fact that you can bring to bear new data sources. In particular, a lot of what we're talking about was enabled by bringing to bear OpenStreetMaps and co-aligning that with the imagery we were trying to analyze. I presented 3 applications in this case: accurate real-time road map alignment, vehicle tracking, 3D reconstruction and georegistration, which was rather abbreviated. This continues to be a rich source of problems and opportunities in the era of data science. So I'd be glad to take questions that you have.
Anyone have questions?
Sure.
You may not have the answer to this, but I'll ask it anyway. So do you have any insight into the interior orientation of the cameras, like a calibration? Because one of the things that I notice is that I look at that misregistration from the metadata, and it appears as if there's definitely something that's not being properly processed with regard to GPS data. One of the problems that people often have is that they don't survey in the location of the GPS date of the GPS antenna on the aircraft, and what you really have to do is align that, or at least survey it into the focal plane of the sensors. So that almost is one of the things that I would check. And have they actually done a calibration on the cameras themselves?
They have to have done a calibration, because without a calibration, things would be way off.
Yeah.
What we got from them was a data stream. So
Well,
this is the data stream that we
Okay,
put out.
and I guess
So
my
the
question
data
is-
stream has the embedded metadata, which
Right.
is the part which we're using for our starting point.
Yeah, I'm just surprised how off those specific.
So the
values are.
GPS and INS, as your pixel resolution grows, you require increasingly high accuracy. So in fact, some of the techniques that you talk about for localization also, the idea is that the GPS and INS systems will put you in the right vicinity, but then the final last stage of the best possible registration is obtained by using image processing techniques.
Did they give a accuracy measure on their errors with regard to it?
So this is a commercial product. I think
Yeah.
the part which I don't really think they provide that type of data, at least we have not found something.
Yeah, I'm just kind of surprised looking at that. Like, wow, that's pretty way off. And very suspect.
So in terms of what people are using in other domains, when we talk about localization, for localization, people are also proposing still computer vision remains the technique of choice, even though you have all these sensors embedded in your sensors and cameras. So the last stage of localization, typically you're looking at trying to do this using computer vision techniques, just because the GPS and IS accuracy will not be the same level that you've got with a high resolution camera.
Well, actually, my question is, through your 3D reconstruction, that generates some interior orientation information of the camera. Is that something that you could have compared to anything that they gave?
They don't give any interior information for the camera. What is included within so the data set is encoded as this NITF 2.0 format. This is a standard. So the imagery itself is in JPEG 2000, and then there's metadata associated with it. The metadata includes the GPS and INS information, but does not have any, as far as I know, does not have anything about the camera geometry.
Any other
My
questions?
question also matters about the accuracy of the map, too, because there's an offset. Yeah, if either one is incorrect, then there'll be an offset.
Oh, you're asking about the accuracy of the map.
Yeah.
So
there
these
could be part of the
maps
difference.
are, yeah. So we've compared the maps with Google Maps. So Google Maps are georeferenced. So you can get the lat long on the Google Maps. And we can look at the alignment of our OpenStreetMap with the Google Map coordinates. And that's fairly good. So it's not that yet that is causing the problems.
Assuming Google Maps is correct.
Yes. Yes. Sorry, I was trying to see whether I had an answer to your question earlier in terms of the shift-based alignment, what that does. In terms of the ransack, I was trying to see whether there was anything in the backup slides, but maybe we'll do that offline.
Okay. Another question, have you looked at for the tracking question, you looked at the potential trade-off between the temporal and the spatial resolution? It seems like you have more spatial resolution than you need to do the tracking. And if you could get 4 Hertz, that would make your tracking much easier, for example.
So that, I think, is now you're talking about design choices within the product platform.
Yeah.
We don't quite have that level of flexibility in controlling what Harris and others are developing. They've come up with this platform, and I'm guessing they had some choices by which they made these observations. What we have come up with is noting the duality between the problems of registration and tracking. So if you look at a sparse vehicular pattern, then possibly a registration technique may face challenges because the vehicular pattern is just too sparse. However, in that sparse vehicular pattern, the problem of tracking becomes easier because you don't have that many vehicles, you can track them easily. Okay? So in terms of formulating the problem in a broader setting, what you'd like to do is when the vehicular pattern is dense, you'd like to align, then track. When the vehicular pattern is sparse, you would possibly like to track, then align the tracks with the road network. So the aligning the tracks would give you more context for aligning, even when there are sparse vehicles. So there's a nice duality there, which we've done some initial work on, but I don't quite have a full comprehensive framework to address.
Okay, any other question?
So that technique where you were using the probabilities for on-road or off-road, did you adjust that for the range? Because I would see that, particularly for oblique imagery, as you go further out, your accuracy is associated with the farther vehicles would be less accurate. So did you adjust the probabilities associated with that?
Oh, we didn't do adjustments. We can do adjustments for the range, particularly when we do the 3D reconstruction. We've got geometry parameters for the scene. When you've got the geometry parameters for the scene, you can do a lot more. So that's sort of next in terms of what we'd like to do is exploit more 3D information. At the moment, we have not done anything of that nature. Yeah. The technique works fairly well even without that adjustment because it's automatically trying to see which are the ones which align well with the road network. So in some sense, this is very well matched with this classic chicken and egg problem, which I outlined earlier. Yeah.
Okay, I think we can thank to Professor Gaurav Sharma again.